Hello, in this video we are going to calculate the MST, but this time we are going to calculate MST using Prim's algorithm, a different algorithm, but again this algorithm also is a greedy approach. Such a type of subset in which all the vertices are present as it were present in the original graph, and some of the edges are selected from the original graph such that these edges make the subgraph is connected and the accumulative weight of all the selected edges are minimum. So that is MST, and we are going to calculate this MST through another procedure. Previously we have calculated it through kruskal algorithm. In this video we are going to calculate same problem with different approach, MST. Prim's algorithm. So let's see how it works. But before going to this MST, let's discuss a concept, priority queue, because there is a use of that thing, priority queue. So what is priority queue? As you know what is queue, you already know what is queue. Normally we have studied it through some array notation, so front and rear. As the element comes, it would store like so on the rear end. So initially F and R are on the same position here on -1, and then as the data populated, the R would move backward on the right. If I am talking about array, it would move on the right hand side, and this way the size of your queue will keep on growing. So that is the normal queue. Here some elements are there. Now how priority queue is different than a simple normal queue. Suppose some data is stored here, 5, 8, 2, 3, 9, 6, like that. So it is order in which order they has come. So in the same order they are placed here in the queue. What does the mean of priority queue? We would associate some priority with each and every element. So priority could be maybe time stamping, maybe the value of this thing, or just put a separate field for that priority value. So if we consider this value as a priority, the value itself, and we would say just if value is minimum, that means the highest priority. Well, in that case, how it works? So this is priority. This is simple queue. And in priority queue, how it appears, like suppose 5 would come first, 5 would be placed here, front and rear would be here, and now if next 8 comes, so since 8 is a bigger value, it would appear here, the rear has come here, and next 2 comes. When 2 comes, since 2 has the highest priority, because after 5, 8 is the value of 8 is greater than 5, so the priority is still the 5 is highest in comparison to 8. So among these two elements, the highest priority is 5, and the next highest priority is 8. So they are they are placed as per their priority. But once 2 comes into the picture, now 2 is the highest priority, so 2 can't be after 8, it should be before, 2 should come before 8. And if we put like 5 to 8, then again 2 is higher priority than 5, so among 2, 5 and 8, 2 is the highest priority. So that would be the picture after inserting 2, front here, rear here. So that is the priority queue. Once the data, if data is itself a priority, the data value is a priority, then that is how the priority queue would work. So we are going to use this concept here in this Prim's algorithm. So that is one thing, the priority queue. And now the notations, G is graph, G is weight, R is some source. In kruskal algorithm we are there is no from our side, from once you are calling function from the main function, or there is no requirement to put the starting point, giving the starting point. But in case of Prim's algorithm you have to specify starting point from which node you have to start. So in this Prim's algorithm you have to provide along with G and W you have to provide the R as well. R means the some starting point. Now starting point could be anything, but normally if we are taking numerical on our answer script, simply put the vertices or node label in chronological order. If it is given like A, B, C, D, E, the node labels are A, B, C, D, then start from A. If node labels are given as 1, 2, 3, 4, then start with 1, but it is just convention, you could start from any point. So now key and pi, these two fields are associated with each and every node. Now if U is a node, if U is a vertices or a particular vertex, then key of U is a field, or you could say a attribute of U, which would put a value. Now this value would a path, path length. So how much you have to pay, or how much the cost of to reach up to you, up to this particular node. So from the starting portion, or how could you reach at U, that would be the minimum cost which is associated with the key of U. So key is a attribute of U which contain a numerical value, and that numerical value reflect how could you reach at U with this cost. Now the next one is pi of U. Again pi is another attribute of U which would reflect, now this value is a label of another node. So from where you come to U, when we are creating our MST. So if this U node is, let's say, some node A, and it is attaching with node U. So if we exploring U after A, and in our final answer, then here pi of U contain A, label of this node. From this node we have reached to U. So pi, you could say parent, but parent is associated with tree. So you could see, like in graph there is no concept of parent, but in tree there is a concept of parent. So pi of U means pi, the parent of node U in MST. So pi of U would be the value of parent of node U, that is A, from where we come to at the node U in the MST. So that is pi, and so all other things are self-explanatory. W of UV means the weight of edge UV, that is denoted by W of UV. Q is simply this priority queue. So the Q is like this, and ADJ of U, that this is adjacent of U. So in a graph, if U is a particular node, so how many nodes are selected, connected with this U. So in this example, the adjacent of U would be A, B, C. All three vertices are connected with U, directly connected with U. So we would say the adjacent of U would be B, A, C, or keep them in any order, but you have to put all three. So adjacent of U would be B, A, C, and I would say adjacent of A would be only U, because A is connected with U only and not C and B directly. So adjacent of A would be only U, adjacent of C would be only U, but adjacent of U would be A B, C. So these are the notations. Now let's see how could we going to calculate the MST through Prim's algorithm. In this slide I have discussed all the components of this algorithm. Now let's take step by step one thing. So in order to calculate MST through Prim's algorithm, let's check the procedure, the manual procedure through what this Prim procedure is going to do. So there's initial point is required, initial source is required from which we could start. So technically we could start from any point, but as the convention says that if the level of nodes are ABCD, then start with A. So in this examples we start with A. So once start with A, we simply consider the edges which is directly connected to node A. So there are only two edges, that is AB of weight 4 and AH of weight 8. So pick the edge which has minimum weight among these two edges. Suppose if there were more edges which is connected to A directly, then we would consider all those edges. So in this case there are two edges are directly connected with node A or vertex A. So we would compare the weight among these edges and pick the minimum one. So there are 4 and 8, two options. We would pick 4. So that would be the scenario. So if we pick the edge 4, that means we pick the node B. So there are two vertices are selected, and obviously this edge between A and B is also selected. So this is that would be the part of our solution, these two nodes and the edge between A and B with weight 4. Now what we consider for the next iteration, we would consider all the edges which is directly connected to A and all the edges which is directly connected to B, but we would not consider this edge which is already selected. So if we considering the edges which is connected to A, so this edge, and this is also connected with A, but since it is selected, so we are not going to select it again. So from A there is only one edge, 8, and from B there are two edges, one is 11 and one is 8. So we would consider these three edges only for the time being and pick the edge which has minimum weight among these three. So 8, 11 and this 8, we would pick the minimum one. There are two 8s, we could go with either of 8. So here in this example this one is selected. So for the next step, we would consider this edge connected with A, connected with B, all the edges connected with B, connected in fact I should say adjacent with B. So all the edges which is directly associated with A, and all the edges which directly associated with B, and all the edges directly associated with C, we would consider all these edges and pick the minimum one. And obviously we are not going to select this edge because it is already selected, and this edge it is already selected, though it is directly associated with A as well as B, but since it is already selected, we are not going to consider it again. So among these edges, this is minimum, so we would pick this one. So up to this point, these four vertices and all corresponding edges like AB, P, C and CI edges are selected, and for the next phase we would consider all the edges which is associated with previously selected vertices. So this, because so all of these edges are considered for the next iteration. So it is because it is associated with A, associated with B, these two are associated with I, these two are associated with C. So that's why these are these edges are under consideration. Now pick the minimum one. With minimum one means the edge with weight, having weight minimum value. So among these edges, 4 is minimum, so 4 is selected. Notice we are not going to see anything with it, whether it is creating cycle or not. We are just considering each and every edges, how it is going to select, how it is ensuring that there is no cycle associated with that. This insurance is from here. See, we are not going to consider any edge which is already selected. So the cycle will not be created. There is no check about, there is no explicit check whether newly elected, newly considered as is going to make a cycle or not. But that implicit check is that we are going to consider only those edges which is or not already selected. Even under consideration, we are considering only those edges which are not already selected. So that is implicitly makes a check that newly considered edge is not going to make a cycle. So after this 4, this again we consider all these edges here after selecting 4. So for next phase, these edges would be considered. Almost all edges. So these edges would be considered, and for next pick the minimum one. So this time this one would be picked. So likewise here we stop. Now take a look on this algorithm. So up to this point, I think there should be no issue. Each and every step is crystal clear. Start from some point, consider all the edges which is directly associated with selected vertices, and pick the minimum one, minimum edge with minimum weight, and this process will keep on going when till the all the nodes are selected. So now what's going on in this algorithm? Let's see. So come back to the first slide here. Now this is R means this starting with A. So there are two fields, key and pi. So there are these two fields are associated with each and every node or vertex. So for initial point for each u belongs to Vg, means for every node of the graph, keep the value of key of u is infinity and pi of u is nil. So for every node put the value for key. Let's say I am putting key k instead of key, so put the value of k is infinity for every node. And pi of u is nil. So let's say put the pi in different color. Let's say pi is. So for every node pi of value will be nil. I am putting n for nil. For source from the starting point, that is the starting point. So key of r is 0 and this would be nil. So the value of pi would be nil, but the value of key is 0 for the initial point. So initially put all the infinity and then explicitly change the value of key from infinity to 0 for initial node only, and it is done once. Now what we do, manually we consider these two edges, because we could see this is a node and this is directly connected edges. But how could we, again, how could we see if this graph is let's say 10 lakh node are there, and since it is not in pictorial form, how could we know that how many edges and which edges are associated with node A, and what would be the weight of these edges? So there could be multiple implementation ways through which we could implement those things, but there should be some concrete way, and that concrete way in this implementation is put a structure of associated with all the edges. So now we would create a queue, a priority queue, in which we would put all the vertices of the given graph. So we have to put all the vertices of the given graph. Now what would be the structure of a vertex? That is this thing, all this information. So structure which would represent a vertex or particular node, and that would having fields label. So for this node, let's say for A, the label would be A, and the key field and the pi field. So label, key and pi, each node having three values: label, key value and pi value. For this node, the key value is 0 and pi value is null, so that would represent one node. And similarly we have to put this structure for all the nodes, and we would put this structure inside this priority queue on the basis of this key. So key would be the value, on that basis we would put the values inside the priority queue. And if all the values of the k values of each and every node, k value means key value, so all the key values of each and every node is infinity except this one, this node A. So once we put all the nodes inside a priority queue, that would be on the top position, on the front position. So if we dequeue an element, that node would be deleted first. So put all the nodes inside a priority queue, and that would ensure, if we put all the nodes inside the priority queue on the basis of key value, that this value would be on the front, and all the remaining value would be, since the key value for all the remaining nodes are infinity, so all would be resides after this A in this priority queue. So once we delete this node, since there is in line number 6 to 11, until or unless our priority queue is not get emptied, we would keep on doing this process. And what we are doing in this process, just extract min. Extract min is this is a term which is used in heap, but since we are not studied heap so far, so I am using the priority queue in generic sense. Actually heap is also a priority queue, but I am using more generic term, priority queue. And extract min would be the deletion of the front, a value at front position. So once you delete this, now each and the remaining all the values having value infinity initially, but we would update these values. How? Let's see. If we pick this value out from the our priority queue, then what we do, we simply check which nodes are adjacent to node U, node which is extracted from the priority queue, in this particular example A. So which nodes are adjacent with node A. Now how you are going to implement that? Hashing could be there, or there are multiple methods through which you could do that. So you have to find out which nodes are adjacent to node A, so in this particular case B and H. So in this data structure, consider B and H one by one, but you could pick any order, first B and then H, or first H then B, it's up to you, but you have to consider each and every adjacent node of extracted node one by one. So in line number 9, 10 and 11, if we consider B as an first adjacent node of A, so the processing of B would be done on line number 9, 10, 11, and after it is done we would repeat the same process for the node H. Obviously these two are related to A. So now if the V belongs to Q, V belongs to Q means V is what? V is a adjacent node. So if we pick B as a V, then we have to check whether B is inside the priority queue or it is outside the priority queue. If it is outside, means it is already selected. So if it is inside, so it is not already selected. It could be a candidate, but it is not selected yet. So if V, that is this, so V once it is considered as P, and then V would be considered as H. So if this B is still in priority queue or not, or immediate after once we extracted this A from the priority queue. So this B is inside the priority queue, and now there are two conditions. So the second condition is whether weight of UV is 4 here. So weight of UV is less than key of V. Now the key of V is infinity right now. So key of B is infinity, and weight of AB is 4, and 4 is less than infinity. So this condition satisfies. See, since B is inside the priority queue and the weight between A and B is less than the key of B is infinity. So these two conditions are satisfied. That means this line number 10 and 11 would be executed. And what is that? It is simply updated the value of key and the pi of this node B. With which value it is updated? The pi value will be updated with A, since we are exploring B through A, so the pi value would be A. So this N would be override with A, and this infinity would be overwritten with the value W of UV. W of UV means this 4. And once it is done inside the priority queue, so it doesn't matter where the position of B were before this updation. Now B comes on the front of the priority queue. Why? Because all the remaining values are infinity. 4 is the highest priority value. So this node B would come on the front of the priority queue. Now, so that is what we done with B. The same process would be repeated with H. So H is still inside the priority queue. So this condition satisfies. Now W of U is less. This again satisfies because infinity is greater than 8. So this again satisfies. So these value would be updated. So from infinity that would become 8, and this from N, nil, it would convert it to A, because we are reaching at H from A. So this value would be updated. And now see the situation of the priority queue. So it doesn't matter where H is resides before this updation. Now it comes to next to the front. So at front value the B would be there because its key value is minimum, that means highest priority. So that would be on front, and at second position, second front position, that node H would be there, and all the remaining node would behind these two nodes. So one iteration of this line number 6 is completed. So as the loop is performing on line number 6, the first iteration is completed. For second iteration, again you extract a node from the priority queue. This time which one is extracted? B. Why? Because it is on the front with minimum value, or you could say the highest priority. So that node would be extracted. Once it is extracted, the same process would repeat again. You would consider all the node which is adjacent to B. So adjacent to B would be C and H. Now since H is not extracted so far, so we would consider H again. So we would consider these two nodes. I would say change some value. So for B, no, once B is extracted, so B would be considered as U and V is considered as once C and once H. So once C, then again the value of C would be the key value and these value would be updated. So this N would be B and this infinity would be 8 because you are coming from the node B to C. Similarly, here the value would be if these conditions satisfy, if W of UV. So W of UV here is 11 and 11 and the key value of is 8. So if weight would be less than key value, then that would be updated, otherwise it is not updated. In this particular case, this is not updated because 8 is less than 11. If 11 would less than 8, I mean the weight of this H would be less than the key value of H, then the key value would be updated. But since it is not so, so these value would not be updated. Only the key and the pi value of C, only the key for node C only the key value and pi value would be updated and not for H. So that would be the scenario, and after this these two values having same priority. So it's now up to you which value you are going to pick. So you could go with any one. So likewise this process would keep on growing and finally you get your solutions. Now could you make any difference because Prim's algorithm and MST, both algorithm are doing the same job, giving the MST, minimum spanning tree. Is there any difference? The difference is, one visible difference is, if you would see the steps of Prim's algorithm, all the components are connected. So whatever answer you have discovered so far, each and every at any point of time the partial solution is connected, while it is not the case in kruskal algorithm. In kruskal algorithm they could be fragmented. Final answer would be a tree, but in intermediate step in kruskal algorithm it might be forest. Forest means all the components are not necessarily connected, it could be disconnected in case of kruskal algorithm, but in case of Prim's algorithm all the components are connected even in the intermediate steps. So that is one visible difference which normally asked in the interview or viva. So that is the complexity of this Prim's algorithm. Since if you would implement this priority queue through binary heap, the complexity of the Prim's algorithm would be order of E log V, and if you implement the priority queue, this queue, priority queue through Fibonacci heap implementation, that the complexity would reduce to E plus V log V. Why I am saying this, it is reduced because in any graph number of vertices are less than the number of edges, and it is actually much less than number of edges if it is a dense graph. So if a graph is dense, then number of edges is quite high in comparison to number of vertices. So anyway, so these are the complexity of the Prim's algorithm on the basis of how you are going to implement your priority queue. So that is all about MST through Prim's algorithm. Thank you.